Hello, everyone. Welcome to the studio. Myself, Abhishek Sangle. I am first year BTech student. Today, I am going to talk about a topic from basic electrical engineering, the double field rolling theory. This topic helps us understand the working principle of single phase induction motor, especially why they behave differently from three phase motors. Double field revolving theory. Welcome to an in-depth exploration of the double field revolving theory, also known as DFRT. This fundamental concept is crucial for understanding how single-phase induction motors operate, particularly their peculiar inability to self-start. We will break down the complex magnetic phenomena into clear, digestible parts, providing a solid foundation for engineering students and electrical technicians alike. Why DFRT is essential. Let's see some points. Single phase limitation. Unlike their three phase counterparts, a single phase supply inherently lacks the ability to generate a truly rotating magnetic field. This presents a unique challenge in inducing continuous motion. Next, pulsating field reality. Instead of rotation, a single phase current creates a pulsating magnetic field. This field oscillates in strength and direction but doesn't sweep around the stator board like rotating field. DFRT provides the theoretical framework to understand how this pulsating field can still produce torque. Explaining torque development. DFRT is the key to explain how a single phase induction motor, despite its pulsating field, manages to develop any torque at all, shedding light on its operational characteristics and a design requirement. The pulsating field's dual nature. The core of DFRT lies in the mathematical representation and subsequent splitting of the pulsating magnetic field. Imagine a single alternating magnetic field. Mathematically, they can express as Bs in bracket T equal to B max cos omega t, where Bs T is the instantaneous magnetic field, B max is the peak value, and omega is the angular frequency of the supply. DFRT states that this single pulsating field can resolve into two equal and oppositely rotating magnetic field, forward rotating field and backward rotating field. Let's see forward rotating field. This component rotates in the same direction as the rotates intent motion and backward rotating field. This component rotates in the opposite direction to the rotors and intent motion. If this conceptual field possesses equal magnitude, precisely half of the main field's peak value, 1 by 2 Bmax, and the both rotate at the synchronous speed ns. You can see in the picture rotation direction and their impact. We're gonna see 2 points: forward fields and backward fields. Forward fields denote as plus ns and backward field denotes as minus ns. The forward field rotate at the synchronous speed ns in the positive direction. That's why uh, we denote as plus ns. This field is responsible for producing the primarily driving torque in the motor. As the rotor accelerates, the relative speed between the rotor and the forward field decreases, leading to reduction in slip. Backward fields minus ns. Conversely, the backward field rotates at the same synchronous speed ns, but in the negative direction. That's why we denote as minus ns. This field generates a braking or opposing torque. As the rotor gains speed in the forward direction, the relative speed between the rotor and the backward field increase, leading to a higher slip. It is the superposition of the two oppositely rotating fields that ultimately reconstructs the original pulsating magnetic field observed in a single phase stator. The zero starting torque conundrum. Understanding the dual nature of the magnetic field it is a crucial for comprehending the single phase motor inability to self start. Forward torque. The forward rotating field produces a positive driving torque on the rotor, attempting to turn into direction of the rotation. Backward torque. The backward rotating field simultaneously produces a negative opposite torque on the motor, trying to turn into opposite direction at standstill. When a motor is completely standstill, both the forward and backward fields exert torque of equal magnitude as a result. These opposite torques cancel each other out, leading to a net torque of zero. This critical balance of the opposing forces means a single phase induction motor cannot initiate a rotation on its own. It requires an external mechanism to provide a initial kick. overcoming the inherent lack of starting torque. This is why auxiliary winding, capacitor, or the other starting method are insensible. You can see the explanation in the picture in short. Slip and torque under running condition. The concept of slip is the vital in understanding motor operation. Slip is the difference between the synchronous speed of the magnetic field and the actual rotor speed, expressed as a percentage or a fraction. Let n be the rotor speed and n is the synchronous speed. Forward slip. For the forward slip, for the forward field, the slip SF is given by SF equal to ns minus 10 divided by ns. As the rotor accelerates in the forward direction, approaches ns, causing SF to decrease. Backward slip. For the backward field, which rotates in the opposite direction, the slip SB is given by SB equal to n plus n divided by ns. And as n increases in the forward direction, the relative speed which backward field increases, causing SB to increase significantly. Crucially, the backward slip SB is always greater than the forward slip SF during operation. The larger slip for the backward field result in the higher losses associated with inducing its less inducting its less efficient and more destructive nature compared to forward field. DFRT, unlocking single phase motor principle. The double field rolling theory is no merely an academic exercise. It's a foundational principle that explains critical aspects of single phase induction motor design and behavior. No self start. Clear explains why the motor lack inherent and start torque due to cancellation of forward and backward field torque at standstill. Shaded pole motors explains the operation of shaded pole motors, which use stand shading of coils to create a rudimentary rotating field for starting. Torque mechanism eliminates the complex interaction between the two rotating fields that ultimately generates the net torque for running operation. Capacitor start justifies the use of capacitor start mechanism to create an initial phase shift producing a resultant rotating field to kick start the motor. Split phase design provide the theoretical basis for the split phase motor where the auxiliary winding helps generate the necessary start torque. DFRT offers a comprehensive explanation for the distinctive characteristic of single phase induction motor, guiding their design and application of various electrical systems. Thank you.